The new images obtained by the James Webb Space Telescope have blown my mind. Rather than expanding our understanding of the universe, researchers have uncovered a disturbing fact in these photographs. This reveals a gap in our ongoing comprehension of the universe's early stages. The theory of the universe's beginning appears to have reached its limits, inspiring us to consider novel theories about its formation. The question arises, how was the universe formed comprehensively? Why does this new revelation challenge even the most esteemed experts in the space industry? To learn more about the Big Bang and the ever-evolving nuances of discovery, we ought to examine the possibility of the Big Bang itself. Instead of the popular belief that the Big Bang was an impact in prior space, it was actually space itself that began around 13.8 billion years ago, alongside matter and time, emerging from a remarkable singularity. A quark describes cosmology in science, where the force of gravity is so immense that space-time becomes infinitely curved. Today, billions of years after the universe began, our celestial home is part of a significant collaboration among experts. This marks a crucial component of the universe's existence. Its ceaseless expansion is essential to recognize. Space does not expand into pre-existing space but is itself persistently growing. Based on established theories, the first stars began to shine somewhere between 200 and 300 million years after the Big Bang, marking the end of the so-called Dark Age. This was when celestial objects clustered together, forming the first galaxies. However, the speed at which these galaxies formed remains a persistent mystery. Significant information emerged from the first images captured by the James Webb Space Telescope in July 2022. Experts discovered that the telescope had detected several galaxies that existed around 300 million years after the universe's creation. Compared to celestial structures that evolved over billions of years, these early galaxies were considerably smaller and less massive. This aligns with the widely accepted scientific model, which suggests that matter in the early universe was not dense enough to form galaxies as large as those observed today. The discovery of 6 remarkably redshifted light sources by James Webb triggered one of the most significant astronomical crises. Despite being similar in age to previously recorded galaxies, these newly discovered galaxies were nearly as large as the Milky Way. This contradicts conventional cosmological expectations. Upon analyzing images captured by the telescope's near-infrared camera, experts confirmed that the light from these objects took over 1 billion years to reach Earth. As a result, these galaxies already existed between 570 and 700 million years after the Big Bang. Surprisingly, they were large enough to defy traditional cosmological theories. Instead of discovering the expected dwarf galaxies, scientists found structures comparable in size to the Milky Way, despite their early formation. If we continue to analyze data collected by the James Webb Telescope, we find that some of these galaxies had a mass exceeding 10 billion times that of the Sun, with at least one possibly reaching an astonishing 100 billion solar mass mark. If this possibility holds, it suggests that there was far more mass in the early universe than previously anticipated, presenting a cosmic riddle. Even if only one of these galaxies is confirmed, it would challenge our prior assumptions about cosmology. To account for these discoveries, the initial density of matter in the universe would need to be several times greater than previously estimated. Another possibility is that these galaxies formed in an entirely unknown and unexpected way. These discussions and discoveries could prompt a re-evaluation of the Big Bang theory. Many space experts with differing perspectives are frustrated, and their viewpoints are frequently debated in scientific journals. Even those who question existing hypotheses are often dismissed as unconventional or controversial. However, it is evident that even strong proponents of the Big Bang theory face unanswered questions. These inquiries include fundamental questions. Why and how did something appear out of nothing 13.8 billion years ago? Could something truly emerge from nothing, or was there a triggering event? Was it all a coincidence? Stephen Hawking suggested that time itself began with the Big Bang, meaning there could be no external cause or precursor event. Another long-standing question concerns the uniformity of the universe. Regardless of direction or distance, galaxies, nebulae, and radiation appear evenly distributed on a large cosmic scale. Modern theorists explain this through the theory of cosmic inflation, though some extend this idea further with the concept of turbulent inflation. According to this hypothesis, inflation has only stopped in certain bubble regions, while elsewhere, the universe continues to expand at an unimaginable rate. This raises a profound question: what if our universe is just one part of a greater whole? Even more intriguingly, what if another universe existed before ours? If this is the case, the Big Bang may not have been a singular event but rather part of an ongoing cycle. Some cosmologists propose that our universe belongs to a much larger, more complex structure. This perspective suggests an eternal cycle of cosmic collapse and rebirth. However, this is not the only alternative viewpoint in cosmology. In 1955, a paper published by NASA implied that the universe may have existed indefinitely, without a Big Bang. According to this perspective, there is no universal expansion. Rather, the continuous formation of matter gives the illusion of growth. Another intriguing but controversial theory arises from quantum physics. Some interpretations of string theory suggest that our universe, and everything within it, might be a projection or simulation existing in higher dimensions. While this may sound like the premise of a science fiction film, it could relate to the Kardashev scale, which measures a civilization's ability to harness energy. If a Type 3 civilization could fully utilize the energy of an entire galaxy, it might have the capability to create a perfectly simulated universe. However, proving such a hypothesis remains a significant challenge. If our universe were indeed a simulation, detecting it would require identifying anomalies, glitches, so to speak, that reveal an underlying artificial structure. Some physicists argue that quantum mechanics itself might hold clues, as the universe appears to function based on probabilistic rather than deterministic rules, much like a computer simulation. Even if the simulation theory remains speculative, it raises profound philosophical and scientific questions. If our universe is an artificial construct, who or what created it? Could an advanced civilization outside our perceived reality be responsible? And if so, does this imply the existence of multiple nested layers of reality, each one simulating the next? Returning to more conventional astrophysics, the discoveries made by the James Webb Space Telescope suggest that our understanding of the early universe is incomplete. The presence of massive galaxies so soon after the Big Bang challenges the standard model of cosmology. If these findings are confirmed, it may indicate that the formation of galaxies occurred much more rapidly than previously thought, or that our current theories about dark matter, dark energy, and cosmic inflation require revision. Some scientists speculate that an unknown force or process may have accelerated early galaxy formation. Others propose that our interpretation of cosmic distances and redshift may need re-examination. If redshift does not correlate as directly with age as assumed, then some of these ancient-looking galaxies might not be as old as we think. This would have major implications for our understanding of space-time and the structure of the cosmos. Another possibility is that new physics beyond the standard model is at play. If an unknown interaction or fundamental force influenced the early universe, it could explain the unexpected size and mass of these galaxies. Some researchers even suggest revisiting alternative cosmological models, such as the steady-state theory or cyclical universe models, in which the universe undergoes endless cycles of expansion and contraction. Regardless of which hypothesis proves correct, the James Webb Space Telescope has already revolutionized our perception of the universe. With its unparalleled ability to observe deep space, it continues to challenge long-held assumptions, forcing astronomers and physicists to rethink fundamental principles of cosmology. As future observations yield more data, we may find answers to some of the most profound questions ever asked. What is the true nature of the universe? How did it begin? And could there be more to existence than we currently comprehend? While these discoveries may lead to more questions than answers, one thing is certain: our quest to understand the cosmos is far from over. The situation is extremely complicated. Investigating the intricacies of cosmology and our universe's beginnings leads us into a realm of deep mystery and ongoing scientific inquiry. The new images that James Webb uploaded to the Webb Space Telescope have rekindled discussions about the very fabric of our reality, evaluating existing hypotheses and causing scientists to rethink their fundamental cosmological concepts. The fundamental understanding of the origin of the universe is a keystone of modern cosmology. According to this theory, approximately 13.8 billion years ago, the universe emerged from a state that was extremely dense and hot, rapidly expanding and resulting in the matter and spacetime as we know them today. This massive event was more than just an explosion in pre-existing space, it included the earliest inception of space itself. The idea of a singularity, in which the force of gravity is so strong that the curvature of spacetime becomes infinite, supports our understanding of this early cosmic epoch. Despite using the James Webb Telescope, assumptions about how galaxies rapidly formed in the universe's infancy are now being challenged. These galaxies, detected within a few 100 million years of the Big Bang, appear surprisingly extensive and developed when contrasted with existing cosmological models. One of the most important questions raised by these revelations is the nature of cosmic inflation. According to the prevailing theory, inflation occurred within a few hundredths of a second after the Big Bang, causing the universe to grow significantly. This rapid expansion would explain the uniformity of the cosmic microwave background radiation observed across the universe today. However, recent discoveries point to complications in the early universe's evolution, which may necessitate adjustments to models of inflation. The development of galaxies observed by the James Webb Telescope compels cosmologists to reconsider the circumstances and processes that govern the origins of the universe. These galaxies are now seen as massive structures existing shortly after the Big Bang, implying a density of matter that exceeds previous estimates. The mystery deepens when considering how such massive structures could form and evolve in such a short time. Additionally, the discovery of these early galaxies raises intriguing questions about the nature of dark matter and dark energy, two elusive components that make up most of the mass and energy in the universe. Dark matter is believed to provide the necessary gravitational framework for the formation of galaxies, yet its distribution and characteristics in the early universe remain uncertain. In line with these astrophysical mysteries, theoretical physicists are exploring alternative cosmological models that challenge the standard Big Bang perspective. Some theories suggest that our universe is only one of many in a vast multiverse, each with its own unique physical laws and constants. Advancements in string theory and quantum cosmology suggest a more complex and interconnected universe than previously thought. One theory gaining momentum is eternal inflation, which suggests that universes continuously emerge from an ever-expanding space. This theory implies that our universe could be just one bubble among countless others, each with its own physical characteristics. The challenge lies in finding observable evidence to support such speculative ideas, as they push the limits of observational validation. Another provocative theory posits that our universe exists within a simulated reality, much like a computer-generated recreation. This concept draws parallels to advancements in artificial intelligence and computational science, where complex systems can be simulated with remarkable fidelity. If true, this idea could fundamentally alter our conceptualization of reality, raising significant scientific and philosophical concerns about the nature of existence. Additionally, advancements in observational astronomy continue to reveal the vastness and complexity of the universe. Telescopes like the James Webb Space Telescope, with its extraordinary resolution and sensitivity, promise to uncover even more cosmic secrets. Future observations may shed light on the very beginnings of the universe, offering insights into its ultimate destiny and the fundamental principles guiding its evolution. Beyond observational astronomy, particle physicists are investigating the fundamental forces that shape the universe. A major goal of theoretical physics is to unify the strong nuclear force, electromagnetism, and the weak nuclear force. Models such as string theory and quantum gravity provide possible frameworks for understanding these interactions at both the smallest and largest scales of the universe. In the quantum realm, the nature of time remains a highly debated topic. Some quantum theories suggest that time itself may be evolving or even illusory. A deeper understanding of time in relation to cosmological models could reshape our comprehension of the universe's beginnings and evolution. Additionally, the search for extraterrestrial life continues to captivate the public imagination and drive scientific inquiry. The discovery of exoplanets, planets that orbit stars outside our solar system, has greatly expanded our understanding of planetary diversity and the potential for habitable environments beyond Earth. Future missions, such as those utilizing the James Webb Space Telescope, aim to analyze exoplanet atmospheres for biosignatures indicative of life. Beyond these scientific pursuits, cultural and philosophical discussions about the universe enhance our understanding of our place within it. Questions about the meaning of existence, the possibility of intelligent life elsewhere, and the future of human space exploration encourage research and dialogue across disciplines. Building upon these profound discoveries and theories, scientists and philosophers alike continue to grapple with fundamental questions about the universe's nature and our place within it. As technology advances, new observational tools and theoretical frameworks are reshaping our understanding of the cosmos. One area of particular interest is the study of high-energy astrophysics, which investigates the most extreme environments in the universe, such as black holes, neutron stars, and gamma-ray bursts. The recent imaging of a black hole's event horizon by the Event Horizon Telescope has provided direct evidence of these enigmatic objects, confirming predictions made by Einstein's general theory of relativity. Yet, many mysteries remain, such as the role of black holes in galaxy formation and the mechanisms driving their immense gravitational influence. Another ongoing challenge in modern cosmology is the elusive nature of dark matter and dark energy. While dark matter is believed to account for the missing gravitational influence observed in galaxies, its exact composition remains unknown. Scientists are conducting experiments, such as those at the Large Hadron Collider and underground dark matter detectors, in an attempt to identify potential dark matter particles. Similarly, dark energy, thought to be responsible for the accelerated expansion of the universe, remains one of the most perplexing issues in physics, with competing theories ranging from modifications of gravity to entirely new forces of nature. The quest to unify quantum mechanics and general relativity is another major frontier. While general relativity describes gravity on large cosmic scales, quantum mechanics governs the behavior of particles at the smallest scales. However, these two frameworks remain fundamentally incompatible in their current forms. Theoretical approaches such as string theory, loop quantum gravity, and holographic principles seek to bridge this divide, potentially leading to a theory of everything that could explain the fundamental workings of the universe. Additionally, the search for extraterrestrial intelligence, SETI, has gained renewed interest with the discovery of thousands of exoplanets. While no definitive evidence of alien life has yet been found, advances in radio astronomy and the study of technosignatures, such as unusual electromagnetic signals, continue to expand our efforts to detect civilizations beyond Earth. The possibility that intelligent life may exist elsewhere raises profound philosophical and ethical questions about humanity's role in the cosmos and how first contact, if it occurs, might unfold. Meanwhile, human space exploration is entering a new era, with plans for returning to the Moon, sending astronauts to Mars, and eventually establishing permanent space colonies. The Artemis program, private space initiatives, and international collaborations are laying the groundwork for long-term human presence beyond Earth. These missions could not only revolutionize our technological capabilities but also provide new insights into planetary science, resource utilization, and the long-term survival of humanity. As scientific advancements continue to push the boundaries of knowledge, the intersection of physics, astronomy, artificial intelligence, and philosophy will shape how we perceive reality itself. The questions raised by recent discoveries, from the nature of time and space to the fundamental fabric of the universe, will likely fuel new paradigms in science for generations to come. Whether through observational breakthroughs, theoretical innovations, or deep philosophical inquiries, humanity's journey toward understanding the cosmos is far from over.